All right, so welcome to lesson 2. So this lesson is about what we call physical quantities. And so you're probably familiar with what a quantity is. And since this is physics, we're talking about what we call physical quantities. So there's 3 learning objectives that we have here. We want to differentiate first the concepts of position and displacement, right? And then distinguish between distance traveled by an object and its displacement. Okay, so we have 3 different terms here: position, displacement, and distance traveled. So they all are very similar. They're related to length, which is a big important physical quantity, but they're all slightly different. So it's going to be really important in your study of physics to understand what's the difference between those 3. And then finally, we'll learn how to perform some unit conversions, which you probably have already done in some other classes before. So some examples of what is a physical quantity. So there's many of them. Like I said, length is one. So the length, the distance, the position, distance traveled. So those are all big, important ones we're going to focus on in this lesson. And we see a few of them in this first picture here, where we see somebody going from a distance of 1 mile, going somewhere, following a certain route. So it's going to be a little bit different what we're talking about as far as the distance traveled, their position. We can see that they have a starting position, that's where the green dot is, and an ending position, and that's where the final dot is. And what we'll learn here is that displacement has more to do with not the distance that you actually took, the path you took, but where you are from where you started. So really, if we were to measure the displacement of this person, we would measure a straight line from start to finish. So we'll go into that more in this lesson. Other important physical quantities we'll learn about is you probably use a scale to measure the mass of something before. There's also, we see time. So it took about 4 minutes and 10 seconds for this person to go 1 mile. So that's pretty good. And so we have an average to give us an average speed here, a maximum speed. So time and speed, average speed are important physical quantities we'll look at. And you probably have had your temperature taken. And so temperature is another physical quantity. And we'll study that in more detail in Physics 152. So these are just examples of physical quantities. All right, then we also have in physics, we refer to fundamental physical quantities, and there are 3 of them: mass, length, and time. And what's interesting about these 3 is that all the quantities, the physical quantities we'll study in this course can all be expressed in terms of mass, length, and time. And so these are some important symbols you'll start to memorize here, because you're going to be using them so much. So so usually we try to symbolize quantities with a symbol that makes sense. So like lowercase m for mass, lowercase l for length, lowercase t for time. Occasionally it doesn't work out that way for whatever reason. Historically, somebody picked a weird letter because another one was already taken. So, right, and so I guess one example of that is the speed of light. So down here we see that it's symbolized with a lowercase c. So a speed is there's all kinds of speeds, and the speed of light is an important constant, and it's about 3 times 10 to the 8th meters per second. So there's some more very precise measurements, but that's what we're going to use when we calculate with things involving the speed of light in this course. We're not going to go use all kinds of digits to do that. So we'll use a nice rounded even number for that. So there's these three fundamental physical quantities, and we could express everything in mechanics. Everything in this course we're going to do can be expressed in terms of these three. So for instance, speed, we see, so for instance, the speed of light, we see there's an m/s. So speed is how much distance traveled. So be a unit of length in a certain amount of time. Okay, so time. So it's length per time is speed. And so you'll notice for the speed of light, the units are m/s. That means meters, m for meters, and I'll do units in green. So meters is the unit we use for length, and s is seconds, the unit we use for time. Okay, so it does get occasionally gets a little confusing because we symbolize mass with m, and we also symbolize meters with lowercase m. So the context is going to be important. And so there's that speed, right? We'd see length per time, meters per second. We would see, for example, also volume would be a unit of length cubed. So we say L cubed, right? Because you have length times width times height. And so if we were to look at the units for that, then we would say it might be meters cubed. Or often you'd hear something like centimeters cubed, cubic centimeters is a common unit you might hear. So there's some interesting definitions. The evolution really of what exactly defines a meter. What is a meter? What is a second? How long is a second? How much mass is a kilogram? And so these quantities, these definitions of what these are have changed over time. So like we saw in the previous lesson, that we're always trying to find a better and better, more precise way to measure something. And so we see this in history, and up until recently, actually, the unit of the definition of mass was actually based on the mass of this. It was a platinum iridium cylinder, and we see it in this picture here, and it's enclosed in a vacuum sealed chamber to kind of preserve it so that over time it doesn't erode and the mass actually changes. And so it was however much mass that was considered a kilogram. And it was up until very recently that it was actually changed. And so there's other definitions that are interesting, like what is a second? It used to be something like 1/86,400th of a mean solar day, something like that. Now it's put in terms of the speed of light, right? So we know that the speed of light goes 300 million meters in a second. So 1 meter out of those three, so one out of the 300 million, 1/300 millionth is a meter. So it's kind of odd, but it's a very precise way to measure it. So as opposed to the previous measurement, which was 1/10,000th the distance from the North Pole to the equator. So nobody actually could have measured that and known, but it was an approximation. And so now we get something more concrete, so that we have a very, very precise definition. And the same with time. I'm sorry, did I say time for related to that? The meter, right? The meter, sorry, is related to the speed of light. So and time, the second, is actually related to the radiation of an atom. So, but if you're interested here, I took a quote from when they actually changed this back in, I think 1983. They actually came up with this more precise definition based on this cesium 133 atom. So the point is, you don't need to remember and memorize these things, but it's just to illustrate how over time we continue in physics to try to make more and more precise measurements and definitions of what something is, right? We have to define something. We have to define things if we're going to talk about them, and so that's part of physics. All right, and so in order to perform measurements, every quantity has to have a unit. Okay, so we can't just say that you weigh 120. Well, 120 what? Kilograms? No. Pounds, stones, slugs. So there's all kinds of units out there, and so if you go to the doctor's office and you get weighed, they usually, at least here in the U.S., they tell me how many pounds I weigh, and I get a little upset every time. And they also will tell me, they'll measure my height for whatever reason. I don't know why. I stopped growing 20 years ago, and they still keep on measuring my height. And they do that usually in feet and inches. And then time, we can measure time all kinds of different ways, right? We have seconds, minutes, hours, days, weeks, months, years. So there's all kinds of different ways to measure time, and there's all different kinds of ways to measure all kinds of units, right? So when we measure length, for instance, if you're driving down the highway in the US, you usually will see miles, right? You won't see meters, but most of the world you'll actually see kilometers. And when you get close to the Canadian border, if you're driving around, you actually see them in both, because Canada will use kilometers rather than miles. And so it's always important to have a unit and be consistent with your unit. So for this reason, there was developed what we called SI units, and it's actually SI stands. It's a French term, Système International, something like that. I don't speak French, but France was a very hot spot in the 1800s for science. That's kind of where science, the place was to be for science was, and that's why French. But they came up with specific units saying that these are the scientific units we ought to use when we are talking about things and measuring things. And so they said for the three fundamental physical quantities, mass would be a kilogram, length would be a meter, and time would be the second. And so these are the base units that we want to use for everything we possibly can for these three. So when you see in especially in your homework, it'll say things like, convert this into SI units. And so SI units, we're talking about these three for the three fundamental quantities. As we go on in the course, we'll find more quantities they're all based on these three, but we'll also have specific, like for force, we could define the units of force in terms of kilogram, meters, and seconds, but we give it a special name, the Newton. In English, we say the pound for force, which we also call for weight. So, but we'll get into that. But it's important to understand these. So although we like to use feet or miles for length, and time, we use minutes, hours, things like that. Especially like when we measure speed, we usually talk about miles per hour in the U.S. But in physics, we're really going to break it down and use the SI unit. So instead of talking about miles per hour, we're really going to get into the practice of talking about meters per second. All right, so so here we're going to get into the three types of forms of length that are important. So length is there's distance, position, and displacement. So we'll look at one at a time. So distance, I have a little definition here. I don't know, forgot where I took from, but it's the length measured from one location to another without reference to anything. Okay, so it's just an overall length in general. And so if you drive from UMass to Boston or Boston to UMass, you might open up the Google Maps and it might show you a route like this, saying, okay, this is the quickest route to get there. And it'll tell you, hey, it's 94.2 miles. So that's the distance you would drive from UMass to Boston, right? Okay, and then it even gives you, how long it's going to take. So from that, we can actually determine what's the average velocity that Google is calculating that you're going to be traveling that whole time. So we'll do that in just a little bit. So now position, also a type of length, but the importance with position is that we're talking about length measured with reference to something, to some location, right? Or we're talking about where an object is located. So every place on Earth has a coordinate. And so if what I did was I dropped a pin on Google Maps on the Du Bois Library here on campus, and it gave me a very precise position of where Du Bois Library is. And so we understand the latitude and longitude, and it's very, very precise, but essentially 42 degrees north and 72 degrees west. But there has to be, if we're going to use north and west, we have to reference some 0 point. And so that's what north, south, east, west does. And so for north, south, right, the latitude, we have what we call the prime meridian. And it's an ancient line that runs through, I think, Greenwich, England. And I think if you go there, it's actually a little tourist attraction. You can see the line going through, and I think it passes through France too. And then, of course, for east-west, we have the equator. And so the 0, 0, if we were to sort of look at the Earth using the prime meridian, the equator, the latitude, longitude lines, then if we thought of it as like a coordinate plane, then 0, 0 would be right here off, I think that's Ghana, right there. So right off the coast of Africa, 0, 0. And so everything up in this quadrant is northwest, everything up here is northeast, down here southeast, down here southwest. And so that's just a way that we reference where something is. And there's some interesting things you could look up if you want about that actual particular location. It's in the ocean, but there's some interesting things there. They actually refer to it as Null Island, even though there's nothing there, it's just water. But there's actually a buoy there that measures things, and it's, I think they actually use something with GPS, and it kind of helps with that 0 point. So I don't know too much about that, but I was reading about it, and it was pretty interesting, things that are out there. All right, so we have distance, right, just a generic, how far something, anything is, a length in general, with no reference. Position, we are talking about we're with respect to a reference point. And then finally, the last part, the third part of of length, we call displacement. And so you may have heard the term displacement when thinking about maybe water gets displaced. And so displacement is the length measured between two reference points, right? And so, or an object's change in position. So if we say reference points, if we say that UMass is a reference point and Boston is a reference point, then it's the length between those points, right? It's this red line going straight from UMass to Boston, right? Well, there's no road that goes straight there, but that would be we could measure that length from UMass to Boston, and sometimes they call it as the crow flies, or as if you were to just take a plane and go exactly straight there. And so I actually found this online, and it turns out it's about 74 miles. Whereas we saw that the actual length you would have to drive was that 94.2 miles. All right. So the displacement that your change in position would be 74 miles. So if you started in Amherst and ended up in Boston, you would say that you are now 74 miles from Amherst. Okay. Or you could say you're 74 miles east of Amherst. Okay. So displacement can be a little tricky because it seems a little weird, but we'll get into that. One last thing I should mention about displacement too is that since it's the length between two reference points, or your change in position, if you were to start in Amherst, drive to Boston, and then drive back to Amherst, right, whether it was a straight line or zigzag, all back and forth all over the place, your displacement would technically be zero because you ended up right back where you started. So that can be a little tricky, especially when we're calculating the difference between average speed and average velocity. All right, so to understand the difference between things like distance, displacement, position, or average speed, average velocity, we need to understand two special quantities called vector quantities and scalar quantities. And so you've probably heard the term vector before, but a scalar quantity, we say that a scalar quantity only has a magnitude. That is, it has an amount. So for instance, an example of it would be distance would be an example of a scalar quantity, because when we said distance, that distance you travel from, if you're going to drive from UMass to Boston, then that distance is 94.2 miles. It only has an amount, a magnitude. So 94.2 to get there, or 94.2 miles to get back. We didn't specify anything with respect to anything else, just the amount. Whereas with a vector quantity, we're dealing with a magnitude and a direction. And so displacement and position are examples of vector quantities, because with displacement, we're saying, all right, now I'm referencing a point. I'm saying if I went from Amherst to Boston, I am now 74 miles east of where I started. Okay, so there's that direction associated with it. So it's not just how many miles, but it's how many miles and in what direction. Okay, and the same with position, because position, we have to reference something. So we're talking about a direction. So like with the latitude and longitude, we're north and west, a certain amount. So there's a direction involved with that. And so there's ways to represent direction. we can say, if we're looking at a map, maybe we could say that if we went from Amherst to Boston, we're left of Boston. Doesn't really make sense though. More makes sense to say we're east of Boston to reference it. But in some situations, we might say right or left or up or down. If we're dealing with actual maps kind of stuff, then east, west, north, south makes a difference. And then mathematically, we have two important ways, plus and minus. So if we were to put a grid, a coordinate plane somewhere, and define a 0, 0, then we can define what's plus and what's minus, what's positive and what's negative. So if we said that 0, 0 was at Amherst, then we could say now if we're 74 miles to the right, we could say we're plus 74 miles. So doesn't necessarily make that much sense with that, but for some things it will make more sense. All right, so we looked at length, the three different types of length quantities, and time is an important quantity we're gonna be working with. And what you need to understand is that there's a difference between what we refer to as time or a time interval. And so for example, if I said at 2 o'clock I have to be at an appointment, then 2 o'clock it's a time. That's just a time. Okay, so sometimes we'll say if you're starting at if you're telling somebody look at a video and I want you to watch something at a certain time marker, right? Maybe at 5 minutes and 25 seconds in, that's a particular time, just one point of time. Whereas a time interval, we're talking about an interval of time, which probably should make sense. And for instance, if you use a stopwatch, like on your phone, this particular stopwatch measured a time interval of 5.81 seconds. Yeah. So it's an amount of time that elapsed, okay, or there was a change in time. And so this triangle sort of shape here with the T, that's the Greek letter delta, right? And we'll use delta in this course to represent change in, anytime something has a change in. So whenever you see the delta, you can literally read it as change in. Okay, so we symbolize time with a lowercase t, but we symbolize time interval with the delta t. All right, and so now we mentioned speed, velocity, average velocity. Well, there's a difference between speed and velocity. Speed is a scalar quantity, and velocity is a vector quantity. Right? Because speed has a magnitude, no direction. Velocity does have a direction. Okay, so if we want to say what's the average speed, and unfortunately for speed and velocity, we tend to use the lowercase v for both, which is a little unfortunate, but for the most part, we'll talk about velocity in this course, and so the v makes some sense. And then I have a subscript here, avg, for average. And one way to distinguish, though, even though that they're both a v, one way we can distinguish between speed and velocity is, you see that there's this little arrow on top of that v for velocity. And so usually when we write a symbol for a vector, we tend to put an arrow over it. Right? That sort of symbolizes that it's a vector quantity. And so you'll see that often if you look in the book, especially or for some problems. So it's not necessary to do, but it often helps to make that distinguish that it is a vector quantity and not a scalar. And so there's a difference between the average speed it might take to get to Boston and the average velocity it takes to get there. So if we were, for instance, to say the average speed, okay, and then I put x for the length, the distance. All right. So we know a speed is a certain distance in a given time interval, and you could use, I mean, you can really use any letter you want. You could use D. I'm going to start with using X, just because when we talk about the different coordinate planes that we use, when you have a coordinate plane, you usually have an XY plane, right? So X axis, a Y axis. We'll talk about a Z axis, which is the third dimension. We won't do too much with that, but we will mention a few things about it, as that'll be important, possibly in your studies outside of this class. But in this class, we're really going to start off keeping things simple, and so we're going to start off with talking about speeds and velocities just in one direction. Okay, so we'll start with talking about them just on the X axis. So sort of like a number line. So we're not going up and down, we're just going left or right or east to west. And so when we do things on the X plane, we usually reference it with an X, and on the Y planes with a Y. Okay. So I'm just going to start with using X, and hopefully that makes sense. And so our X, or our distance, is at 94.2 miles, and I'll put MI for miles. And the time interval is 1 hour and 47 minutes. Okay, so I am going to say, let's figure out what is this in miles per hour. What's the average speed in miles per hour? So what I'll do is I'll just say, I'll put that 47 minutes, I'll divide it by 60 just to get it as a fraction of an hour, so it's easier to deal with mathematically. So it's about 0.78 of an hour, and I'll add so the 47 minutes is 0.78 hours plus the 1 hour, so about 1.78 hours is what it takes, according to this, when I took the image of this. So it's obviously it changes with time because of traffic. So we'll divide the 94.2 miles by 1.78 hours, and I get about 53 miles per hour. So I guess it's not all on the Mass Pike going 65 or 85, what people do. There's a lot of stuff getting to the Mass Pike and traffic and whatnot. So Google actually calculates that. It's actually using the data that you have in your phone as you're there at a certain location, and timing how long it takes you to move from different coordinates along the Mass Pike. And every single where you are, if you have Google on your phone, then it's using your data to try to determine this. So it's a little bit invasive, but it's also helpful too for planning. All right, so that's the average speed. You drive 94.2 miles, take in an hour and 47 minutes, and you average 53. Obviously, you're not doing 53 the whole time. So the average velocity, though, so you notice the difference between these two equations that we've written. And besides the arrow, the only other difference is that instead of saying X, I put delta X. Okay, so X, right? So speed is a scalar quantity, so we just care about the distance, right? Your car is putting 94.2 miles on your car driving that length. But with velocity, it's a vector quantity. Okay, so velocity is not distance traveled in a certain time interval, it's displacement. Okay, so you could read this as change in x, or we could call it displacement. Okay, so it's where you started, it's the distance from where you started to where you ended up, just a straight line, shortest possible route. And so for this, if you recall, I'll set this up here. So when we looked at that image, let's see, oh, it didn't say there, but I wrote it down. It was 74 miles, according to that website anyway. So your displacement is 74 miles. Still the same time interval, 1.78 hours. Okay, so now the 74 divided by 1.78. Now I got, I'll round that to about 42 miles per hour. Okay, so it's a little odd to say that because you actually drove 94 miles. So that can be a bit tricky. People tend to have trouble with that when they're doing average velocity. Okay, but if you think about it, you're not, when we say average speed is 53, you're not doing that the whole time anyway. So that's just an arbitrary number as well. Okay. Could we also figure out, let's say you could go 60 miles an hour the entire way, right? Not possible, but let's just pretend. So if you could go, then how long would it take you to get there? Could we figure that out? Well, we can just use a simple algebra, right? We could say, well, if average, let's just do speed. If the average speed we want it to be 60, right? We know that the distance we got to go is 94.2 miles. Right? We can rearrange and solve for time. So if we do that, we can solve for time interval is going to be the distance traveled over the average. Pardon me, I have dyslexia, so I'll often write things backwards. So time interval, the time it's going to take to get there, it's going to be the distance you got to drive, the 94.2 miles, over your average speed. So we'll say 60 miles per hour. So if I do 94.2 divided by 60, I get about 1.57 hours. And of course, that's kind of like, well, what is 0.57 hours? Well, it's a little over half. But if I do, let's see, 0.57 times 60, that'll give me 34 minutes. So basically 1 hour and 34 minutes. Okay, so I suppose if you sped when you could, you probably could do that. Okay, so then the last thing we'll look at for this lesson is converting units and unit consistency. All right, so what I didn't really do here is show you why this miles divided by miles per hour turns into an hour. Okay, but perhaps you already have done this before, and you know, with a fraction, that if you have something in the numerator and the denominator, they'll cancel out. And then if you have a fraction in the denominator, then the denominator in the denominator goes to the numerator, right? So the hours goes up top. All right, so there's some useful conversion, unit conversions, and that you could keep in mind. I took this one from your textbook. One we use a lot, 1 inch is 2.54 centimeters. A mile is 1.609 kilometers, or sometimes it's nice to know in meters, it's 1,609 meters, right? That's easy though. That's the nice part about the metric system, is that it's just basically moving decimals, not this weird conversion factor. Okay, and that's probably the most, these two are probably the most useful ones, I think. If you want to skip some steps, I suppose, in your calculations, in your assignments, then some of these other ones might be useful too. But it's good to try to do a little bit of practice and get into the hand of it, because converting units and keeping your units consistent is important, because it can really help you as you're solving problems to identify any particular mistakes you might have made. So we'll go through some examples of what that is, but I just don't want you to, I mean, you could Google everything, right? You can just type in how many inches or whatever. So that's fine, but you're really gonna miss out on some of the actual thinking that's gonna come out of it. So I hope that you will choose to try at least to do some of these conversions, because it's really going to make your life easier in this class if you do them by hand and not just Googling everything. Okay. So let's do an example of what how we might convert a unit. So let's say we have a speed of 4.50 kilometers per hour, and we convert it to units of feet per minute. And we're given that 1 meter is 3.28 feet. So what I'm going to do here is I think the way to kind of do it nice and clean so that it's easy to visualize when things are canceling out is I'm going to take this kilometer km slash, right? The slash just means per kilometers per hour, and I'm going to turn it into a nice fraction like they taught us to make in whatever, 4th grade or whatever it was when we started doing fractions. And then we know that 1 meter is 3.28 feet. So if we want to get this, we could do a couple steps here. So we could say, in order to change the kilometers to meters, well, you might know you just need to move the decimal over 3 places. Well, isn't that the same as saying dividing by 1,000, or sorry, multiplying by 1,000? There's 1,000 meters in a kilometer, right? And if I set it up as a ratio like this, nice fraction, 1,000 meters in 1 kilometer, then we notice what happens. Our kilometers cancel out. And then we could see, all right, what are we left with? Minutes per hour. Okay, well, we're sorry, not minutes, meters per hour. So we're starting to get there. We turn it to meters. And you could, if you wanted to, multiply this out and do it again, or you could just keep on going. You could just place all these ratios together and just go through it all at once. So that's what I'm going to do. And so we're given that the 1 meter is 3.28 feet. And so you might say, well, how do I know do I put the 1 meter on top or on the bottom? Well, you look at, what are you trying to get rid of? You're trying to turn the meters into feet. So in order to do that, you want the meters to cancel. So we would put the meters on the bottom so that they would cancel. And then we're left with 3.28 feet on top. Okay. And now, yay, we're feet per hour. So now we just got to go from hours to minutes. Okay. And So our hours initially is in the denominator, so we'll put it in the numerator here for our conversion, so that will cancel out. We know in 1 hour there are 60 minutes. Our hours will cancel out. We'll see that everything's canceled except for feet per minute, which is the units we want to know. And now it's just simply a matter of doing the math. So we'll multiply the 4.5 times 1,000. Right, we don't need to divide by 1 because you know why. Times the 3.8 and then divided by 60. Okay, and I get 246. My color's right, so. Feet per minute. All right. Okay, and so what might you do if say you had to do something like, say you wanted to convert maybe cubic centimeters into cubic inches. So say I had 5 cubic centimeters, and I want to know how many cubic inches that is. Okay, well, it's pretty much the same thing. We'll multiply by the ratio. Okay, so I'll put, since there's no per there, we'll just put over 1, just so it looks like a fraction. I know for me, I still recall in first semester physics of this class when I took it. I still recall putting that fraction over a 1. That would help me kind of visualize what cancels, right? Because anything over 1 is just the anything, so it doesn't really change anything. And so that's kind of the beauty of doing it this way, right? Is that there's one of the questions in the homework that's called the magic of 1, right? Because anything over itself is 1, and so often we can use that, and we will use that in this course to manipulate things to make our lives easier, or make our calculations easier. Okay, so now I say, okay, well, I want to get inches cubed. All right, so how do I get inches cubed? Okay, so I guess first of all, I should fix this. This is not what's going in the conversion factor. That's what I want to get. I want to get how many inches cubed is that? And so what we're going to do is we'll use the same conversion factor, that there's 2.54 centimeters in 1 inch. Okay. And then we're going to cube that whole ratio. Right, we'll use a different color for the cubed. So we're going to cube that whole ratio. So that means we're going to cube the 1, we're going to cube the inch, we're going to cube the 2.54, we're going to cube the centimeters. Okay, and then we'll see that we'll be left with 5 cubic centimeters over 1 times, say 1 cubed is 1, inches cubed is inches cubed, 2.54 cubed. Where's my cube thing on this calculator? Oh, let's do this. Okay, I get about 16.4, I'll round it off to, and then centimeters cubed is centimeters cubed. Okay, and then we see that centimeters cubed cancels, and we're left with what we want, the inches cubed. So basically we divide the 5 by that 16.4, and it rounds to about 0.31 cubic inches. All right. Okay, and then just to point out, we have unit prefixes, which I'm sure you've used plenty of times. And probably the biggest ones we'll use are probably be in these three here: kilo, the centi, the milli. And so we see that it's 10 to the, in whatever scientific notation, right? And then K for kilo, C for centi, M for milli. So if I were to say a kilometer, or sometimes we say kilometer, we know that the unit for a meter is M, and for kilo is K. So a kilometer would just be KM. Occasionally we'll use micro and nano. So if we want to say a micrometer, or sometimes we say micrometer, that's a tool to measure, but it would be this is the Greek letter mu times n. Right, so if we have 1 kilometer, 1 micrometer, right, if we want to put that in scientific notation, it'd be 1 times 10 to the 3 meters. Okay, if we wanted to put micrometer into scientific notation, 1 times 10 to the minus 6 meters. So it's a good thing. You'll start to remember these. You won't have to look all these up all the time, but every now and then you'll get one like, you might not be familiar with micro or nano. That's okay. You can look that up. I know like pico and femto, I always have to double check. I'm pretty sure it's 12 or 15, and but it's good to just check, right? So it's good to consult a chart. Okay, and then finally, I want you to, every time you are approaching a question, you should always ask yourself, once you're done, does this make sense? Does my answer make sense? I know it's really, you really want to like rush through and get it done and be like, "Ooh, I'm done. The torture's over." But especially if you're doing an exam or something where you're going to lose points, then you want to make sure you think about it. Okay, and so this is a useful chart to have, because we're not accustomed in the United States to think in terms, what is a kilometer? Okay, even I do physics, and I have a hard time thinking about how kilometers and miles are related. Sometimes I'll read something, I'll talk about kilometers, and I'm like, which way does it go? Is it less per? So it's so a chart like this is good to be handy, right? And so we know that a meter, right, a meter stick and a yard stick are about the same. So we could say that a meter and a yard, or a meter, is about 3 feet. Okay, not exactly. We're not going to use this for precise calculations, but it can really help us get us a good idea of, does this make sense? Okay, and then the meter per second, 1 meter per second is about 2 miles per hour. So you might think to yourself, okay, maybe you're doing a calculation, you're calculating the average speed of a car, and what if you get 100 meters per second? Right? You can quickly look and say 100 meters per second. Well, the miles per hour is about twice as much. So it'd be about 200 miles per hour. Okay. You might want to think about, well, this is a car. The problem is probably not, going to be messing around with funky numbers. It's going to give you reasonable numbers as far as a car's speed. And so unless it's the problems maybe asking you about car at the speed track with a professional speed, these crazy cars that go crazy, then if you're talking about just somebody just regular driving, then you might want to reconsider, say, does that make sense? Okay. All right, so that'll kind of help you out a lot as you go through this course. Okay, so at the end of each lesson, before we review the learning objectives that we started with, I'll also point out to you some the questions on the homework that are related to this lesson, directly related. So after doing this lesson, you might want to take a crack at problems 3, 4, and 5. Okay, and then I put either the problem number or the name of the problem that it's called in Mastering Physics. I put it there just so that, it's probably a good idea to try to, now that you just did this lesson, go take a look at those. So it's up to you though. And then if there's any extra example problems, I'll put them on this page as well. But I think we did some pretty basic stuff. Did a lot of examples in this in this lesson. So I don't think you really need any more examples. But if you do, you can definitely go to office hours or come to the live sessions, and we'll do some more. All right, so we had 3 learning objectives. The first one was to differentiate position and displacement, right? So position, right? It's where an object's located, okay? It's here or it's here, right? Maybe we use the latitude and longitude lines. Maybe we use a coordinate plane. Okay, it's here, it's at one specific point. Whereas displacement is how far you are from where you started, your change of position. Okay, how far you are between the reference points. Then we learned to distinguish between the distance traveled and the displacement. So we said even though if you drive your car 94.2 miles along the Mass Pike to get to Boston, well, you really only displaced yourself in your car by 74 miles. So a little odd, but it'll get a little, just taking time getting used to that idea. And then we learned to perform unit conversion by using this ratio of units. And so I just did an example here of this. And maybe you might want to do something like this over 1 just to kind of help you visualize. If that helps, if you know how to do this, then don't worry about it. Do however it works for you. Okay, this is how it worked. I recall it working for me. And then, look at your units. Cancel out your units as you go along. And this will kind of help you make sure that you did what you were supposed to do to get the answer you were looking for. All right, so that is lesson 2. I'll see you again next time for lesson 3.